Greetings, everybody. Welcome back to Organic Chemistry 2, Lecture 2 via Zoom. We're going to focus principally today on organic synthesis and do a synthesis review. Starting with ethanol here. I've come up with a system I hope works. I'll be working here first as indicated by the asterisk, and I'll do my work over here so I can make it big and then shrink it to the box. Ethanol needs to become ethylene. Little bookkeeping here. This carbon loses the OH. This carbon loses an H. That's dehydration, HOH. To do such things, we typically use sulfuric acid. And heat. And we saw that back in chapter 10. Chapter 10.5, acid catalyzed dehydration of alcohols. Yep. Gonna have to be careful with my work area here. Bear with me. New stuff again. All right, we'll shrink that down so it fits in the box. All right, moving on. Oh, that's right, section 10.5 right here. And now we're going to talk about taking an alkene and treating it with chemicals to make it into an alkyne. This specific alkyne is acetylene, also known as ethyne. What happens there is we're going to replace H's on each end with a pi bond in the middle. I don't think we have ways of doing that directly. But if I can put a halogen on each side, that means I can do an elimination reaction on each side. And each time we do an elimination reaction, we make a pi bond. So halogens on each side, that's one of our earlier reactions in chapter 6, halogenation of alkenes, and that was 6.1D. 6.1D. Oh. And we're going to follow that by double elimination. Do an E2 times 2 using excess strong base and heat. And we got that in 9.3. So how do we do a halogenation of an alkene? We can use Br2 in step 1. That would make a vicinal dibromide. The word vicinal meaning on adjacent carbons, if you recollect. And 2, if I use a strong base and heat, I can eliminate each of those alkyl bromides and make alkenes or make new pi bonds. Now, if I choose this base, nice, strong, bulky base, use excess, then I don't have to worry about a third step happening. That would be the deprotonation of a terminal alkyne. This base is not strong enough. Terminal alkynes have a pKa of 25, and this would make an alcohol. This base here would make an alcohol, which is a pKa less than 25. So we would not have that happen. So here's the answer to this box here. Oh, the one got cut off. We can still make it smaller. There we go. Okay, we've made an alkyne. And now the thing I wanted to avoid in step 2, I want to happen here. I want to deprotonate a terminal alkyne. That's a chapter 4 reaction. And we learned how to do that. We did that on our review the other day, the one that got lost. The good people at Zoom are working on that now. We may recover that video. I tried to make a replacement video for it earlier today and found out my new system with my old program, the audio does not work. I will have that fixed by the end of the weekend. All right, simple acid-base reaction as done in chapter 4. Gives us a acetylide. That's the conjugate base of acetylene. That's when we started talking about synthesis, if you remember, in chapter 7. This next reaction is a chapter 7 reaction, which we reviewed again in chapter 9. It is no less than the classic SN2 reaction. So if we wanted to make sure we got a very good yield, we could even add a solvent like DMF to make the yield better. And before we go too much further, I'm going to make sure we have a blank version of this on page 1, which we clearly don't. And the answer's on page 2. I'll go back and edit out the answers we did before. Okay, what are you going to get when you take an anion here with a lone pair and a backside attack on a carbon with a halogen? Well, you're going to get a sigma bond between two new carbons. That's called synthesis, isn't it? And the result will be a molecule that looks like this. Triple bond, CH2, CH3. There we go. So here we have, if you had to name it, you would say 1-butyne. Okay, that was a chapter 7-9 reaction. This is a terminal alkyne. We learned that you could add water to those in chapter 7. We learned that if you put the oxygen on the more substituted carbon, like this one, this being the more substituted carbon here, and 2 new H's on the end, this is now a CH3 where it used to be a C with 1 H. That's a form of hydration, and there was a tautomerization involved. The remainder of today's lecture, we're going to just do mechanisms for all these steps. So we'll be doing that so you remember how these things work. That was the one where we had to use a mercury. So we're now here working on this box. We had to use mercury. It was a mercury 2 plus ion in the form of mercury 2 sulfate. Water was needed as both the solvent and the source of this oxygen right here. And we needed an acid reagent and catalyst. Catalyst for the tautomerization. Reagent to get rid of the mercury in a step called protonolysis. And this guy is going to go here. Oh, not if I'm not careful. There we go. Nope, it doesn't go there. It goes here. Brings up the point. Oh, don't move the whole thing. I got to grab the orange thing. All right, so there we go. We have a phone call. I'm going to pause if I can. Sorry about that. I'll make sure that doesn't happen again. I'll be right back. I'm back. Sorry. Red Cross wants blood. All right, we're resuming our video here. Sharing our screen. And where were we? We're trying to get this orange thing off of here. Crush fingers. There. We're going to work on that one next. This one accomplishes the same end in that it adds water to the molecule, but it puts the, oh yeah, I forgot my original mistake, didn't I? This is the one that goes here. That puts the O on the more substituted carbon. This is the one we're working on with the O on the less substituted carbon. We learned methods of putting an O on the less substituted carbon of a pi bond in both chapter 6, where we did it with alkenes, and chapter 7, when we did it with alkynes. And in both instances, we used boron to accomplish that result. So chapter 7's version, which was found in 7.5. Both of these are found in 7.5. They go together. So I'll just put a big old 7.5 right here. And here we used a special version of boron that you might want to review. Sec isoamyl. There's two of them on something called borane. Borane is BH3. So we have di-sec-isoamyl borane, and that puts a hydrogen on the more substituted carbon. And do you remember why? The reason was H is more electronegative than B. Not normal for H, but in this case, 2.1 for H is the electronegativity, 2.0 for boron. So we get an H on the more substituted and a B on the less substituted. And then we can trick the molecule into having an oxygen where there used to be a boron if we use hydroxide and peroxide, hydrogen peroxide. Other peroxides work, but that one is cheap and it works well enough for us. I don't think I got the 2. It's okay. We'll put a 2. Oh, that's a small 2. It won't let me do it. Work in progress, as I'm going to say a lot this semester. Okay. So where are we at? We've got aldehyde here called butanol, ketone here called butanone. And those seem to be dead ends, so let's move on. Before we do this one, or this one, let's, there's another loose end here, ethyl bromide. That's this guy. Where'd it come from? Oh, you can make it from an alcohol. Most reliable method is the one we reviewed the other day, PBr3. And that was found in section 10 point, I think it's 10.4b, 10.4b. Okay, now we're back over here. Terminal alkyne becoming an internal alkyne. That's a new carbon-carbon bond there. That's called synthesis. How do we go from an alkyne to put a carbon-carbon bond there before? Step 1, we took a proton off the alkyne. KH, good base. And we're not here anymore, we're down here. But I think I can write the answer straight there. That's going to deprotonate our terminal alkyne, pKa25. And then I need to put what's called a benzyl group. It's not a phenyl. It has a phenyl in it. phenyl with an extra C. Benzyl group. Might as well use benzyl bromide. And there we have our synthesis of our internal alkyne. We can do things with that. I think we should review those too. I just don't have them here yet. We did reductions of those molecules, didn't we? We'll do that shortly. How do we make an alkyne into an alkene? That's just what I was talking about here, reduction of alkynes. Let's do one here and add a couple more here. You can use one that goes with syn addition or one that goes with trans addition of H. For a terminal alkyne, it doesn't matter. You will never see the difference. So reacting an alkyne with sodium metal and NH3 as found in section sodium and ammonia reduction of alkynes 7.6. Gives an alkene. Since we're on the subject, if we did sodium and ammonia here, you would get this result here, a transalkene, also 7.6. Okay. And how do you get a cisalkene? Since we're down here, we had a couple methods. One was use BH3 and acetic acid. Another one was H2, palladium on calcium carbonate, also known as chalk, and lead sulfate combination at the bottom below H2 is known as Lindlar's catalyst. Lindlar's cat, not to be confused with Schrodinger's cat. And this one gives cis alkenes, which would be right here. Ethyl down, benzyl down. All useful reactions. All will be used again in chem242. Okay. Also, 7.6. 7.6 down here. So I have that already, but I don't have it over here. All right, how do we make our alkene into an epoxide? We had a couple ways there. That's a chapter 11 reaction. That was near the end of the semester. Does not make it less important or more important. Epoxide synthesis was in 11.3. 11.3. And we used chemicals like this one, CH3CO3H. That's peracetic acid. Or we could follow a protocol using an old reaction we studied in chapter 6. We could first do halogenation in the presence of water. That makes a vicinal halohydrin. That has a bromine on the less substituted carbon and an alcohol on the more substituted carbon. And then if you treat that alcohol with a base, doesn't even have to be a special base. NaOH makes the alcohol into an O-, which does an intramolecular displacement of the halogen. And it gives an epoxide. Both methods, very reliable methods of making epoxides. Hope you can read that. Doesn't have to fit the box, does it? Okay. Epoxides are useful for synthesis too. That's why they ended up on this review. We're going to make a carbon-carbon bond using a strong nucleophile. We already looked at strong nucleophile called acetylide here. Strong nucleophiles, when they encounter epoxides, go for the least hindered carbon. The least hindered carbon being this one on the bottom. We're going to get a new carbon-carbon bond there to acetylene. And it's going to look like this. Here's the synthesis part. CH2 goes to a C that has an O-. I'm not going to write the minus because something happens in step 2 to the minus. An O- will protonate using HCl, and you'll have an OH. And that's in the wrong box, isn't it? It's going to be fun. Moving that out of the wrong box. I don't even know. Do it piecemeal. It doesn't like me moving small things, does it? Listen, you guys can have fun watching me fix my mistakes all semester. We're going to redraw that bond, aren't we? Ah. There. And where did we learn about opening of epoxides? That was one of our last things. Reactions of ethers, 11.5. My computer's ignoring me because my pen got turned off. Opening of epoxides. What does PCC react with? We learned that PCC can convert a primary alcohol to an aldehyde. You learned that in chapter 10. Okay. Let's see, PCC oxidation of alcohols with chromium, 10.6. And then our HB-Sia2, we already have the section number for that. Where's HB-Sia2? Yeah, I'm losing it. There it is, 7.5. 237.5. And what happens there is you convert your terminal alkyne into an aldehyde, just like we did above right here where I can't see it. So we're going to have an aldehyde. Let's draw it down here. Goes to a C, C. Here's the synthesis bond. Here is the C with the OH. Oh, it's not an OH anymore. PCC did what to a secondary alcohol? We have a CC goes to a C. That's a carbonyl. PCC converts secondary alcohols to ketones. So there is our molecule. Yeah, I don't think we're gonna get the whole thing without getting other stuff. Maybe. That goes right there. And I believe this is a logical stop for our first segment. I'll save this and render the video. And let's do it correctly this time. I have to stop my share, and I bid you adieu for 5 minutes. Maybe a little longer. The longer these videos go, the longer the render takes. So 5 to 8 minutes, let's say.